Hello everyone. I want to go continue with our trees. So I'll remind you quickly what a tree is and how we will from now on very often talk about rooted trees, although I gave you at the end some examples like isomers, which are not rooted trees. But so very often we have a rooted tree. I'm just going to take an example here. And I'm going to do a special type. Let's do this one. Okay, one more. Okay. That's my tree. Okay, so this, so a couple of things perhaps. So this is the root, right? The root. And then the guys that are all the way at the end, the ones that have no more parents, they have no more children. So these are what we call the leaves. And the other ones, the parents, if you want, including the root, are sometimes called internal vertices. So let me call them all, make pink as well. I know the root is a bit more different, but still, the root is a bit special because it's the only one that has no parent. But for the rest, every vertex, except for leaves, they have children, right? And therefore, we call these internal vertices. So there are leaves and internal vertices. So these are the vertices. So there are two types of vertices, right? So these are the types of vertices. So we're going to do a little bit of counting as well. So I'm going to already get some numbers here. So the number of leaves, I call that L. The number of internal I will call I, and the number of vertices I will call N. Okay. So in this case, what are the values here? So L is 1, 2, 3, 4, 5, 6, 7. I 1, 2, 3, 4, 5, 6. And N is, the sum of the two, right? 13, because you're either internal or you're a leaf. So our first formula, we're going to have two formulas. Well, not always, but so what the first formula that we have is that the vertices are either leaves or internal. So the sum of the leaves plus internals is the total number of vertices. Now we have already seen one other thing here. We know that the number of edges is one less than the vertices. And that's how we can, if it's not a rooted tree, we can still recognize it as a tree by just counting. It's not just a property, it's defining property. At least when the tree is connected, if it's a tree connected, right? So now what the arity? I'm sorry, guys. So the arity, that is the maximum number of children that a root can have, that a vertex can have, an internal vertex can have, because leaves cannot have children anyway. So leaves, of course, have no children. And you see here that everybody else has two children. So the arity is 2. Now, there could be, here's an example of let me modify the tree slightly. I'll return back to this tree, but I want to just show you. This is also, well, sorry, perhaps I should keep the levels, right? This 2 is a tree of arity 2. But there's something special here. So again, if we would mark this would now be a parent, an internal one, and the other one would be a leaf. Okay, the counts are different now, right? So I'm not going to adjust the counts here. I'm going to go back to the original one. But it's the case that there is one guy who has only one child, where the others all have 2 children. So this is also part of being arity 2. However, we are going to be interested in the case that we just had. So I'll return to that case, where everyone has exactly 2 children or no children. If you leave, you have no children, otherwise you have 2 children. So that is called a full, so a tree of arity 2 is called a binary tree. Okay, so a full binary tree means every internal has 2 children. And of course, leaves have no children. So it's either 2 or 0, but otherwise, if you want to put it that way. Now, that is for binary, but we can do this for any number. So let me just give you an example of a full ternary tree. I'll draw it quickly. So how would that be? Well, it would have to have 3 and then 3 here, and perhaps another 3 here, and this guy also has 3, and perhaps this guy also has 3, and then this guy also has 3, and let's stop there. So just to show you that it doesn't have to be symmetric in no way. So you see, so there are quite a lot of guys that have that leaves, and then there are quite a lot of guys that have that internal, and those internal ones all have 3 children. So this is a full ternary tree. Okay, and so this, would this be a full ternary tree? No, because this guy only has 2. For a full, if you add the word full, then everything has to have 3 children. Everything that has children, everyone that has children has to have 3 children. Okay, let me get rid of this again. So let's again mark our leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the number of leaves is 13. Remember that's the colors, right? Oh no, let's put it here. Leaves. Then we have the internals. Perhaps I should make them green, right? Okay, let's make them green. Keep the colors of the trees, right? So 1, 2, 3, 4, 5. I is 5. So we know also what n is. What is n? The sum of both, 18. We don't have to count. Okay. Okay, before I get to a formula, because there's going to be a formula, let's consider one more thing, because we talked about it, the level. So what are the levels here? So we have level 0, level 1, level 2, level 3, and level 4. And so the number of the biggest level, so is the height. Perhaps rather than talk about level, let's talk about the height. So the height here is 4, because we have that, which also means this is the same as the longest path. That's also what it means, right? Well, sure, yeah, the longest downward part. Because because of course I can walk up first and then go down, but the height is the longest downward part. In other words, the longest part that starts at the root. If you don't want to say downward, just say longest part starting from the root, and that is 1, 2, 3, 4. There's 2 actually. Okay, that's the height. And what is the height here? 1, 2, 3, 4. Oh, I forgot. Oh, so good thing that I did this, because now I notice this, and otherwise I would give you a formula and the formula would not work, and then we would say, oh my god, what's happening? Okay, so here the height, let me record this, the height was, what do you say, 1, 2, 3, 4, also 4, height is 4. But there is no, it could be, in general, trees can have quite some serious height. Okay, so we have a full binary tree, and this is a full ternary. Okay, so now assume that we are here. These 2 formulas that I have so far are always. So this is any tree. It has these 2 formulas. But now comes a formula. This is only true for full M-ary trees. M-ary trees. So the arity of the tree is M. M is 2, 3, 5. We'll do examples. Okay. And then we have the following very nice formula. N is equal to Mi plus 1. Now let's see how we come to this count. Well, first of all, there is the root. Let me make it in a bit, let me circle the root to make clear that it is slightly different than the others, right? So this is the root. So that is one guy. Then we have the other internals, Okay, and every of these internals, no, sorry. Yeah, sorry, let me say it that way. Every internal has m children, right? So, okay, so in total, how many children are there? I mean, people that have a child, let's call a child somebody who has a parent, right? Well, there are I, remember, internal means to be a parent. There are I parents, and each parent, full emery, this full emery means every parent has exactly m children. So in total, there are going to be m times I, the product rule, right? M times I, these are the number of vertices that have a parent. Now, why is it not everybody? Because the root doesn't have a parent. So we didn't count the root, but everybody else is in that situation. And did we double count anybody? That's, of course, we can do the product rule if they are independent. But if perhaps we should adjust our formula if we have overlap. But no, because you have only one parent. So if we count here I ranges over all the possible parents, and then m is ranges over all the children of that particular parent, then nobody can be listed twice because nobody has more than one parent. That's exactly the root, the tree property. So this is the number of children, people that have a parent, and plus 1 because we have also the root. So that's our formula. So let's verify this formula. Does this match here? So I'm going to calculate it here. So what does the formula say here? N, what is N? 13. Is that the same as M, the arity? So M is the arity here, right? So is that 2 times I plus 1. So that checks. Here, what is the formula? How does the formula read? Well, 18 should be equal to 3. That's now the arity times, again, we had 6 internals plus 1. Okay, so that's not true. What did I do wrong, people? What did I do wrong? Perhaps I didn't. Wait. 1, 2, 3, 4, 5, 6. That's a leaf. That's a leaf. These are 3 leaves. These are 3 leaves. These are 2 leaves. I see. You see what I did? I adjusted the number I, but I forgot to adjust this one, right? It's the sum of the 2. It's the sum of the leaves plus the internals, so that is 19. Well, so good. 19 is, so now it checks out. Okay, that was a silly mistake. So that's a formula that we have here. Now I'm going to use this here, and here is, perhaps I should have started with this before I even started talking about trees, because it's something that you would not expect that you can use trees. So I don't know whether you know what these chain letters are. A chain letter. These come and go sometimes. In some periods they are more popular than other periods. Nowadays with social media, so I guess people don't do letters that much anymore. Although it's the same as a chain email. That could replace it by that. But let's say traditionally a chain letter was this. It said, okay, very often they contain wishes of good wealth, good health, and prosperity, and so. And it says you have to share your prosperity and your happiness with others. So for you to be prosperous and healthy and happy, you have to submit. You transmit the same message that you have gotten in this letter to 5 more people. So chain letter says it depends, 5, 7, depends on what the original setup was. I'm going to do the example of 5. So chain letter says send 5 copies to your friends. Okay, so involve your friends, make sure that they hear it. Nowadays, perhaps we do tweets and retweets or something like that. But it's important that we follow the practice here. If you're gonna respond to this letter, then you're gonna send 5 copies, not more, not less. That's the only assumption I have to make here. Okay, so suppose you do this, and now, of course, it could be that you get this letter in the mail and you send it to your friends, and then one of your friends doesn't, and another 4 do, and then so on. You don't know what happens anymore, and at some point you get the letter again because somebody thought he should send a letter to you. Now, there are actually some better forms of this letter keep track of to whom is already sent. So they always say send it to 5 copies to new friends, to your friends not on the list. Yes, people that have not gotten a letter yet. So in that way we are sure that nobody gets more than 1 letter. Okay? So, okay, that's the setup. I hope everybody understands what is going on. But here comes the very surprising thing. At the end, so at some point this thing stops, right? At the end, let's say 100 people got a letter. So 100 people, wait, we say, oh no. Okay, so I'll do a couple of things. So let's do a couple of questions on this type. So first, assume 100 people did not comply. How many letters were sent? You say, wait, Professor, that's not enough information. 100 people did not apply, but we also need to know who got the letter, and how are we going to find this out? Okay, I'll do a couple of more similar things, but let me show you that you can figure this out. First of all, what this has to do with trees. I hope that is clear to you. The graph here it's a directed graph if you want, but you think of it as a tree. You are sending a letter to 5 of your siblings, 5 of your children, 5 people, 5 of your friends get a letter from you. So this tree so somebody started this guy and then sent it to 5 of its friends. 1, 2, 3, 4, 5. So okay, so let's do this. So okay. And they all very much like him, and they say, okay, we will do it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You see already some logistical problems when we want to keep the levels. There are going to be a lot of vertices, right? So it gets a little bit messy sometimes. But okay, for now let's stick that. Okay, so this was a guru, and the guru sent this to his loyal disciples, and they say, of course we will send this to 5 more people. But those people, some of them say, you know what, this is one of these pyramid scams, I don't believe in that. So let's say the second guy says, okay, I'll do it. But and also the last guy says, okay, of these guys. I'm not going to draw everything. So, but for instance, we have this guy says okay, this guy says okay, but the other 3 say no way, forget it, I'm not doing this silly thing, and so on. I don't want to say how it ends, right? But you see how the tree is. Each time you either send nothing, right? Because remember, I said when you do this, if you follow the instructions, if you read this letter, you either decide to follow the instructions and send out 5 copies. And the fact that you are sending it to nobody on the list means you're not sending it to anybody that has already received the letter. So it can never have a loop back, would make it not a tree, right? So that guarantees it's going to be a tree. Or you decide, I'm not doing it, and then you don't send it. So it's not that somebody says, okay, I don't really believe it, but let's just send one letter. What can that hurt me? Okay, so that not. So what does this mean therefore? The fact that you either send 5 or 0. This is exactly the description of a full M5 quintary 5 array tree. So this is a full 5 array tree. Okay? So we were getting into the realm of my results here, right? I can apply, these two I can always apply, but perhaps I don't need them, but this one I can now apply. Now, what information do we have? It seems we don't have enough information, right? Because we don't know how many people got letters and or did not get letters. Well, we got one information, 100. What is 100? 100, let me list a few of the 100 people here. Here, this is one of the 100, and this is one of the 100, and this is one of the 100. These are the people that do not comply. So these are, therefore, the leaves. Because if you comply, then you have 5 children. And if you don't comply, you have nothing. You're a leaf. So this tells me that L is 100. Okay. All right. Okay. So, what do we have now? All right. So let's look at our two formulas. The edge formula doesn't play. So I'll make it, these are the two formulas I'm going to work with. The first formula is always true, but the second formula is only true for a full M-array tree, which is the case. Okay, so what do we have? We don't know n yet. Okay, that's actually the question. How many people, assume 100 people don't comply. Oh yeah, but the question was how many people, so how many letters were sent of, let's see, what is it, yeah, how many people sent a letter? So what are we asking? If I ask how many people sent a letter, what are they? These are exactly the non-leaves, okay? So the question is, L is 100, what is I? We don't know what I is. The internal ones. The internal ones are exactly those that sent a letter. So the question is asking how many people sent letter. It says exactly how many people are internal, because internal means that you have children, means that you have sent a letter. Okay. So given this, do I know that? Now it seems that we are missing information, right? We don't know what n is. So n is what? Well, let's see. We have this one formula. We have the two formulas. Let's use the two formulas. So n is L plus I, but I know what L is, so that is a 100 plus I. But there's another formula for n, that is this formula. N is also equal to m times I plus 1. But I know what m is. M is the arity, it's a full M-array tree, so that is 5i plus 1. Now I have an equation here. So let me write it up. What is the relevant equation? I can solve for I, because after all, that's what I'm after, right? So how do I solve here? Well, bring the 1 to the other side. So let's okay, I'll do it so that nobody gets like minus 1 here, and then I do minus I, right? So on the right hand side, I have 99 is equal to 4i. Okay, so what did I wrote wrong here? 5i plus 1 is n. What did I do wrong? Okay, I'm sorry. I'm a little bit lost here what I did wrong. because the reason is that I have to be a whole number, right? So why if I'm uh, I see. Yes, yes. I'm sorry. Um, I read the question wrong in the textbook. In the textbook, it was about four letters to send instead of five. Now, in other words, what this says, it's impossible for a chain letter like that to have 100 people not to comply. It's also weird because why is it impossible? You see, because the number here doesn't work, right? I is not a whole number. So I have to adjust the number here a little bit to make sure that it works. So let's say there were 101 people. Sorry, but the mistake comes from I misread the question. And therefore I used the wrong numbers. So assume there are 101 numbers, okay? So the only thing I'm changing is the 101 here. So this becomes 101, okay, let me shape it like that. So this becomes 101. So now we get 100 equals 4i, and I see that I is 25. So that means that 25 people have sent out a letter, and 101 did not. Okay, so how many people were involved in total? Well, we can also calculate n. We can now calculate everything, right? There were 126 people involved in this. 126 people have seen the letter, are involved in this scheme, let's call it. So let me clarify why there was a little hiccup here. It's if you have a situation like this, like let's say a full M503, there are only certain numbers that can occur as the number of leaves. Okay, in fact, to be precise, let me tell you this, it has to be divisible by, the number has to be divisible by, what am I saying here? No, I cannot, there's no good rule for it. There's only certain numbers that work and other numbers don't work. Okay, so let's consider a same situation, but now say assume 40 people complied. And let's include the root in that, including the root. The guy that originates, yeah, of course, he does it, right? He tells himself, you have to do this, and he says, okay, I'm doing it. Okay, so 40 people complied. Again, the same question. Now, question is, okay, how many people involved in this? So how many people saw the letter? I don't want to say received the letter because the root, of course, never receives a letter, but I want to include the root. So how many people involved? How many people saw the letter? Either sent it or at least received it. Okay, so what is that? So let's what are the numbers that we have? So we have n, l, and I, and of course we also m, but that is still 5. Okay. What do we know? What is this 40 referred to? The people that comply. That means the people that have sent out a letter. These are exactly the parents. These are the internal ones. So this is 40. Now, there's always two quantities that we don't know. And it seems strange to not know two quantities, but it's because we have two equations. Two equations with two unknowns are always solvable. But of course, it has to be an integer solution. And that was where I got a little bit hung up. So we have here n is 5. Let me copy the two equations. 5i plus 1 and n is l plus I. These are the two equations. So what we have in this case, n is 5 times I, that is 200 plus 1. So we know actually already what how many people are involved, 201. We actually don't need to know the number of leaves, but I could have asked how many people involved, how many refused. Right, let's calculate this now too. So this is now n, we know what n is, because this formula already gives it right away to us. What is the other formula tells us? Well, we know that there are 201. We don't know what the number of leaves. The number of leaves, this would be L, right? This is n, but we're asking, here we're asking what is L? Well, that is L plus, n is L plus I, and I is 40. So we see that L is 161 here. Okay? All right, so let's do the same. I'll do the example from the book. So a chain letter requires 4 copies to be sent. Okay, and so here's the example now. Assume 100 people did not comply. How many did comply? And when I say did comply, I sent the letter, so including the root. Okay, so same question, but now the actual question where it should have been 4 and 3. So again, let's write all the quantities. M, that is 4, N, L, and I. Let's see, what do we know? Why do I put that we know this? We don't have to question this. So what is this number? The 100. The people that did not comply are the leaves. So I know what this is. What is this asking? How many did comply? That's the ones that did send letters. That is I. So we need to know I. Okay, I write down my 2 formulas again. N is L plus I. The number of vertices are, every vertex is either a leaf or an internal. But the way formula is this one. That is, M is 4 here, so 4I plus 1. Okay, so let's copy what I have. So we also have this one, 100 plus I. Okay, so we have these two are equal, right? There's two different ways of writing n, so I'm equating these two. So I have 100 plus I is 4I plus 1, so that is 99 equals 3I. Therefore, I is 33. So 33 people did not comply. So we can also see how many people were involved again. Well, it's the sum of 133, so 133. So the point is, if you know that you're in a full emery tree, then you need to know only one of the 3 quantities, the number of vertices, the number of leaves, or the number of internal vertices, to calculate the 2 others. So keep that in mind. We'll do some questions on that. And the book presents actually formulas for each of them, but I think that's not necessary, because it's much easier then you have to memorize. Well, okay, you don't have to memorize because it's open book, but I like to better always work with the same formula over and over again. These are the 2 formulas, and I don't need anything else. Don't distract me with other formulas. I don't want to know them. I'll find them. These are the 2 that I want to work with. This is my formulas that I use. Okay. So then there is another notion. Let's see, how much do I say? The notion of a balanced tree, I'm not sure that I want to talk about that too much. The one result I want to show is, so we have an M-array tree, not necessarily full. And h is the height of the tree. Remember, this is the longest path from a root to a leaf. If you think of a genealogical tree, it's the number of generations back that it goes, right? So that is the height of the tree. And then we have an estimate for the number of leaves. So given these 2 things, it's not an equality, it's an inequality. That is this inequality. Okay. Now I'm going to leave the proof for you to read in the textbook because it's a proof by induction, and it's a very nice proof actually, where you just work your way down. So, but for instance, you can use this now to the following thing, right? Suppose now let's give an example. What could I? Let's just give a simple example. Suppose you have a three-array tree, or let's take a binary tree. Why not a binary tree? No, okay, binary. No, let's take a binary tree. So we have a binary tree, not necessarily full, of height 7. Well, do I have one here? Oh, this was a binary tree of height 4, right? Okay, we had something here. This is a binary tree of height 4. Right? So let's look at that example. Binary tree of height 4. What is the maximal number of leaves it can have? So the number of leaves is less than, binary means m is 2, 2 to the power 4. So at most 16. How many did we have? This particular one had only 7. Now, you will say perhaps it will never happen. Well, let's make a tree where you have exactly 16, and that is a tree that is in all the leaves have height 4, and it's a full binary tree. So it would go this way. No, that's not enough. I have to do more. 1, 2, 3, one more. Okay. So I'm drawing a full binary tree, and this is how this would look like, right? Let's see whether this works. This is this guy, this guy, this guy, this guy, this guy, this guy. You see, it's not always easy to draw this nicely. It takes a little bit of, if you're going to do this on a test or so, you're going to have to practice and redraw it a couple of times because you always end up with too little space at the end. But notice this is a full binary tree. Oh, what did I do here, people? I don't know what I did here. So, okay, it is true, but I don't know. It's these two, right? Yeah, now it's a full binary tree. Okay, now it's a full binary tree. No, yeah, because this is accidentally erased. Okay, and it has exactly 16 leaves. So it really. So in other words, to get the maximum count is when you have a very symmetrical tree, a tree that where every leaf has the same length and it's a full tree. Okay. Okay, there is something about balanced tree. I don't want to go in there. I'm going to stop here. I'm going to make homeworks for you to try this out, and then might do a quiz on this counting because it's a nice thing that you can use trees in counting, like things like chain letters or something like that. It would think of that way. Okay.